Have you ever heard about altermagnets? These are a newly discovered class of magnetic materials, stirring up quite the buzz in the scientific community. What makes them so special, you ask? Well, altermagnets boast a unique blend of characteristics that set them apart from their conventional magnetic counterparts like ferromagnets and antiferromagnets. Imagine a material that embodies a dual nature, resembling both an antiferromagnet with zero net magnetization and a ferromagnet with non-relativistic spin splitting. This is precisely what altermagnets are. Such a peculiar behavior emerges from the intricate interplay of atoms within the crystal structure of these materials. In essence, altermagnets are like a coin with two sides, marrying the properties of antiferromagnets and ferromagnets in one. They are not just a scientific curiosity, but also a fascinating subject of study that could revolutionize our understanding of magnetic materials. Intrigued? Well, there's a lot more to learn about these fascinating materials. Now you might wonder, what makes altermagnets so special? Well, the magic lies in their distinctive attributes. Unlike conventional magnetic materials, altermagnets display a unique fusion of characteristics. They embody a dual nature that defies the norms. On one hand, they resemble antiferromagnets, exhibiting zero net magnetization. On the other hand, they mirror ferromagnets, displaying non-relativistic spin splitting. One of the most intriguing properties of altermagnets is their unique spin polarization. But what exactly is spin polarization? Imagine a crowd of electrons, each spinning in its own little world. Now, if a majority of these electrons begin to align their spins in one direction, we say that there is spin polarization. In altermagnets, this spin polarization is quite noteworthy. It occurs not only in the physical arrangement of atoms, also known as the real space, but also in the momentum space. This is the abstract space where we consider the distribution of electron spins within the material. This unique behavior of spin polarization in altermagnets stems from the intricate interplay of atoms within the crystal structure. It's like an impeccably choreographed dance, where every move of every dancer, or in this case every atom, contributes to the overall spectacle. But why should we care about these properties? Because they're not just intriguing, they're potentially transformative. Altermagnets could play a pivotal role in the field of spin caloritronics. This is an exciting field of research that explores the interplay between spin and heat flow. It holds potential for developing new technologies for information processing and storage, something that's not achievable with conventional ferromagnets or antiferromagnets. In a nutshell, altermagnets are more than just a new class of magnetic materials. They are a testament to the wonders of nature and the boundless potential of science. They challenge our understanding of magnetic materials and offer a new perspective on how we can leverage these properties to advance technology. These properties are not just interesting, they could have significant applications. So, where could we possibly use these altermagnets? Well, this is where things start to get really interesting. You see, these altermagnets could potentially play a pivotal role in an emerging field of research known as spin caloritronics. Now, the term might sound a bit intimidating, but don't worry, we'll break it down. Spin caloritronics is essentially the study of how spin, the intrinsic angular momentum of particles, and heat flow interact with one another. It's an exciting field that's still in its infancy, but it's already is showing promise in a range of applications. Imagine a world where we could harness heat, one of the most abundant forms of energy around us, to process and store information. It sounds like something out of a science fiction novel, right? But with the help of altermagnets, this could become a reality. When altermagnets, with their unique blend of properties, could potentially enable us to control the flow of both heat and spin in a material. This is something that's simply not achievable with conventional ferromagnets or antiferromagnets. So, how does it work? Well, the unique spin polarization in altermagnets means that a majority of electron spins tend to align in a particular direction. This alignment can be influenced by changes in temperature, creating a link between thermal energy and spin. In other words, by manipulating the temperature of an altermagnet, we could potentially control the spin of its electrons and therefore the flow of information. It's a concept that's as fascinating as it is complex and could revolutionize the way we think about data storage and processing. But of course, this is just the beginning. The research into altermagnets and their potential applications in spin caloritronics is still in its early stages. There's a lot we don't yet understand about these intriguing materials and their distinctive nature. The potential of altermagnets in this field alone is vast and exciting. To truly understand altermagnets, we need to dive a little deeper. Let's take a journey into the world of crystal effects, specifically the crystal Nernst and crystal thermal Hall effects. These intriguing phenomena were at the heart of a recent scientific study, where researchers explored the thermal properties of a unique altermagnet, rubidium dioxide, or RuO2 for short. Rubidium dioxide was chosen as a representative of altermagnetism, a new class of magnetic materials that are making waves in the scientific community. But why this focus on crystal effects, you may ask? Well, these effects are a direct result of altermagnets' distinctive magnetic nature, and they offer a gateway into the intricate connection between thermal and magnetic behaviors in these materials. Let's start with the crystal Nernst effect. Picture this. As the material experiences a temperature difference across its dimensions, a voltage emerges. But this isn't your everyday voltage, it's perpendicular to both the temperature gradient and the magnetic field. This tells us that the material's magnetic properties are influencing its response to temperature changes. Now let's move on to the crystal thermal Hall effect. This phenomenon is a thermal version of the well-known Hall effect, where a voltage is created perpendicular to the direction of current and an applied magnetic field. In the thermal version, a temperature gradient is created instead of a voltage. The crystal thermal Hall effect occurs due to the spin-orbit coupling in the material, which is a key characteristic of altermagnets. These investigations into the crystal Nernst and crystal thermal Hall effects in altermagnets like rubidium dioxide are opening new doors to understanding the complex and beautiful dance between thermal and magnetic behaviors. They are helping us to unlock the true potential of altermagnets in spin caloritronics and ultimately in our everyday technology. This is just the tip of the iceberg when it comes to understanding the fantastic world of altermagnets. So, to summarize, altermagnets are not just another type of magnetic material. They stand out with their unique blend of characteristics, defying conventional norms by embodying a dual nature. They are remarkably influential in the exciting field of spin caloritronics, hinting at a future of new technologies for information processing and storage. The study of crystal Nernst and crystal thermal Hall effects further unravels their intriguing thermal properties. The journey to fully understanding and harnessing the potential of altermagnets has just begun, and it's a journey worth keeping an eye on.